Ever been on a video call when your laptop suddenly heats up and everything freezes? That's not just bad luck. Our devices are hitting real physical limits. For decades, we made computers faster by shrinking their components, cramming more transistors onto chips. Moore's Law in action. But now, we're building at atomic scales, and electrons are crowding the highways, generating heat and wasting energy. This heat isn't just annoying, it's the main thing stopping us from making faster, more powerful computers. As AI and data demands explode, our electricity-based computers are reaching a breaking point. Data centers now use as much power as small cities, and the energy cost is skyrocketing. We need a new, sustainable way to compute. The answer? Harnessing the fastest thing in the universe, light. Let's break down how your computer works. At its core, it's billions of tiny switches, transistors, flipping on and off using electricity. Electrons flow through microscopic wires, but as they move, they collide, creating resistance and heat. That's why your phone gets hot, and why data centers need massive cooling. No matter how small we make things, electrons always generate heat and face resistance. The more we demand, the more energy and cooling we need. An unsustainable cycle. Imagine trying to send 1 billion messages through a crowded hallway. Chaos and slowdowns are inevitable. We're at the limit. Shrinking things further risks meltdown. To break through, we need a new kind of messenger, one that doesn't get stuck or tired. Enter light. If electrons are the bottleneck, what if we used photons, particles of light, instead? Imagine a world where information moves at the speed of light, literally. This idea isn't just science fiction, it's the foundation of a technological revolution that could change everything we know about computing. Photons have no mass or charge, so they travel at light speed without resistance or heat. Unlike electrons, they don't bump into atoms and lose energy, which means they can move data faster and more efficiently, with almost no energy wasted as heat. This is the foundation of photonic computing, using light pulses instead of electrical signals to process information. It's a radical shift, replacing the flow of electrons with streams of photons, opening up new possibilities for how computers are designed and how they function. Light can zip through microscopic channels on a chip, carrying data with incredible speed and efficiency. These optical pathways can transmit vast amounts of information in parallel, far beyond what traditional wires can handle. Scientists have dreamed of this for decades, but miniaturizing lasers and lenses to chip scale was a huge challenge. The precision required to manipulate light at such a tiny scale pushed the limits of engineering and materials science. Now, breakthroughs in materials and nanofabrication are making practical photonic circuits possible. New techniques allow us to bend, split, and guide light on chips smaller than a fingernail, bringing the dream closer to reality. We're at a tipping point. Working prototypes show photonic computers could be orders of magnitude faster and more efficient than anything before. These advances promise not just incremental improvements, but a leap forward in performance and energy savings. This isn't just a faster computer, it's a new architecture working with physics, not against it. By embracing the unique properties of light, we're reimagining what computers can do and how they can transform our world. Harnessing photons could unlock new frontiers in AI, science, and sustainability. Imagine data centers that use a fraction of today's energy, or AI systems that learn and adapt at unprecedented speeds, all powered by light. The age of the electron is fading, the era of the photon is dawning. The future of computing is being rewritten, and it's brighter than ever before. So, how do you make light do math? It might sound like science fiction, but it's a real and rapidly advancing field. Imagine harnessing the speed and purity of light to perform calculations that would take traditional electronics much longer. Surprisingly, it's simpler than it sounds. Instead of relying on streams of electrons, photonic computing uses photons. the fundamental particles of light, to process information. First, data is converted from electricity to light using a tiny on-chip laser. This laser acts as the engine, generating precise pulses of light that represent digital information. The light pulses travel through waveguides, miniature fiber optic paths, etched onto the chip. These channels guide the photons with incredible accuracy, ensuring the data moves exactly where it needs to go. Along the way, microscopic lenses and prisms bend and split the light, directing it through a maze of optical components that manipulate the signals. These components perform calculations as the photons move, using the unique properties of light to add, subtract, or even multiply data streams at the speed of, well, light. Multiple beams of different colors can travel the same path without interference. This is called wavelength division multiplexing, enabling massive parallelism and allowing many operations to happen at once. This lets photonic chips handle many calculations at once, dramatically increasing speed and efficiency compared to traditional chips. The result is computational power far beyond what electronics can do, opening new possibilities for artificial intelligence and data processing. At the end, a photodetector converts the processed light back into an electrical signal so it can be used by the rest of the computer system. The result? A specialized coprocessor that solves complex problems almost instantly, making it ideal for tasks like machine learning and scientific simulations. And it does all this using just a fraction of the energy required by conventional electronics, making it a greener solution for the future. Light does the heavy lifting, carrying information at incredible speeds and with minimal loss, and the rest of the system reaps the benefits, ushering in a new era of ultra-fast, energy-efficient computing. Switching to photons isn't just a small upgrade, it's transformative. Photons move at light speed, so calculations happen almost instantly. They generate almost no heat, slashing energy use and cooling costs in data centers. Imagine AI systems 100 times more powerful, using a fraction of today's electricity. Photonic chips can process multiple data streams at once, thanks to parallelism, something electronics struggle with. This makes them perfect for AI, big data, and scientific simulations. Light signals also stay cleaner, with less interference than electrical signals, boosting accuracy. For critical applications, science, finance, medicine, this precision is a game changer. The result: faster, greener, and more reliable computing. The future is bright, literally. In 2025, a University of Florida-led team made a breakthrough, a silicon chip that uses light for AI's core math. Their chip integrates microscopic Fresnel lenses onto standard silicon, letting laser light perform complex calculations, like convolutions for image recognition, at almost zero energy cost. Tested on AI tasks, it matched the accuracy of traditional chips, but used up to 100 times less power. This isn't just a lab demo, it's built with existing manufacturing methods, paving the way for real-world use. Major chip makers could soon integrate this tech into future designs, the leap from theory to a practical blueprint for next-gen computer chips. The age of optical AI is here. Light is no longer just a dream, it's powering the chips of tomorrow. Despite the hype, big challenges remain before photonic computers go mainstream. The biggest, memory. Storing data as light is tough. Photons don't like to stand still. Most systems convert light back to electricity for storage, creating bottlenecks and energy loss. True all-optical memory is still a research frontier. Precision is another hurdle. Photonic chips need nanometer perfect alignment, and even tiny vibrations can throw off calculations. Making these systems robust for real-world use is a massive engineering challenge. Integration is key. The near future is hybrid, combining electronics and photonics on a single chip. Solving these puzzles will take innovation and teamwork across disciplines. So, when will you get a photonic computer? Not next year, but sooner than you think. The first wave will be hybrid systems, with photonic coprocessors alongside traditional CPUs. Data centers will adopt them first, making AI faster, cheaper, and greener. High-performance workstations for science and engineering will follow. As costs drop, photonic tech will trickle down to consumer devices. Think gaming PCs and premium laptops within a decade. A fully all-optical computer is still a long-term goal, awaiting breakthroughs in photonic memory. But the momentum is real. Chip-based optics will soon be in almost every AI chip. Even if you don't see a powered by light sticker, your tech will be running faster and cooler behind the scenes. Imagine a world where lag and overheating are history. Computers respond instantly, opening new possibilities. Tasks that once took minutes or hours are completed in the blink of an eye, and your devices always stay cool and efficient, no matter how demanding the workload. Doctors could diagnose diseases in seconds. Scientists could simulate climate or medicine with unprecedented detail. Medical breakthroughs would accelerate, and researchers could tackle complex problems with tools that keep up with their imagination. Photonic computing could slash the energy footprint of our digital world, making data centers greener and more sustainable. Imagine entire server farms powered by renewable energy, running cooler and quieter, while supporting the world's growing demand for information. AI could become a tool for solving humanity's biggest challenges: clean energy, food security, and more. With faster, more efficient computing, AI could analyze vast data sets in real time, helping us make smarter decisions for the planet and its people. Self-driving cars and AR glasses could process data in real time, safely and efficiently. Cities would become smarter, transportation more reliable, and our daily lives seamlessly connected to the digital world around us. Creative tools would become more powerful, unlocking new forms of art and expression. Artists, musicians, and designers could push the boundaries of creativity, bringing their visions to life with technology that never holds them back. The very limits of what's computationally possible would be rewritten. We'd enter an era where innovation is limited only by our imagination, not by the speed or power of our machines. Moving from electrons to photons isn't just a tech upgrade, it's a leap toward a smarter, more sustainable civilization. This shift could transform every industry, from healthcare to entertainment, and redefine what technology can achieve. The breakthroughs are real, and the future is being built now. Every day, scientists and engineers are pushing the boundaries, turning science fiction into reality. The next time you see a beam of light, remember, you're looking at the future of computing, a future that's brighter, faster, and more sustainable than ever before.